this section, we're going to learn how to solve a system of equations by using inverses. For example, if you have 2x plus 3y is equal to 5, and x minus 2y is negative 1. How would you solve this by using inverses? Well, let's define the coefficient matrix. It's 2, 1, 3, negative 2. I'm ready to write down the format to get the answer. xy is going to equal to the inverse of A times the right-hand matrix. It's the inverse of the coefficient matrix times the right-hand side number. So I just need to figure out what A inverse is. But A is a 2 by 2 matrix, so finding A inverse is somewhat routine. This product is negative 4 minus this product is 3. So it's negative 7. And then you play the switching game. The 2 and the negative 2 get switched, and the 3 and the 1 stay where they are, except the sign changes. I'll distribute the negative to all the numbers inside the brackets. So it's 2, 3, 1, negative 2. That is A inverse. So I take A inverse, 1/7 times 2, 3, 1, negative 2, and multiply it by the right-hand numbers. Multiply it by 5, negative 1. And it's probably always friendliest to do the scalar 1/7 multiplication last. When you multiply the first row or dot the first row with the first column and only column, you get 10 minus 3 or 7. When you take the second row and you dot it with the first and only column, you get 5 plus 2, which is 7. And when you do 1/7 times 7, you get 1. And when you do 1/7 times 7, you get 1. So x, boom, 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 is equal to 1. Y equals 1. We solved our first system of equations using inverses. Just find the inverse of the coefficient matrix and then multiply it by the right-hand number and go on to the next problem. It's that simple. Okay. Let's try another one. Suppose you have 2x minus 3y is negative 4, and you have x plus 2y is 5. So how much is xy? Well, it's the inverse of this coefficient matrix times negative 4, 5. So let us find the inverse of the coefficient matrix. Well, it's 4 minus a negative 3, which happens to be 1/7 again. And then you switch the 2 2's, and you change the sign of the negative 3 to positive 3, and the 1 to negative 1. So you get 1/7 times 2, 3, negative 1, 2. And that's A inverse. That's the inverse of the coefficient matrix. So xy is equal to the inverse of the coefficient matrix times the right-hand numbers. Negative 4, 5. The 1/7 multiplication I'll do at the end. When you do the first row with the first column, you get negative 8 plus 15. Get 7. And then when I multiply or dot the second row with the first column, you get positive 4 plus 10, 14. And 1/7 of 7 is 1, and 1/7 of 14 is 2. So just copying down xy equals 1, 2. X is 1, y is 2. We haven't talked about this for a little bit. This just isn't completely random things. X equals 1 and y equals 2 is the only pair of numbers that lie on the first line. X is 1. 2 times 1 is 2. Minus 3 times 2 is 6. 2 minus 6, it actually does equal negative 4. That is 1, 2 lies on the first line. And it has to lie on the second line as well. X is 1. 2 times 2 is 4. Is that 5? Of course it is. 1 plus 4 is 5. Trying to find out the x and y values that will make the equality symbols true in all the equations. In this case, 2 equations. Okay, we're going to try this now with a 3x3 matrix. Suppose you had the system of equation x plus y plus 2z, y plus z, x plus y, and it equals 3, 1, 1. Suppose you had this system of equation. The coefficient of x's are 1, 0, 1. 1, this has 0 x's. You shouldn't be afraid of adding 0. And the next row has 1x. Y's, positive 1, positive 1, positive 1. That is 1, 1, 1. Z is positive 2, positive 1, and 0 z's. That is 0. 2, 1, 0. Okay. Now, I'm going to tell you that the inverse of this is, I've already calculated it. It is 1/2 times 1, negative 2, 1, negative 1, 2, 1, and 1, 0, negative 1. Okay. So I have the inverse of the coefficient matrix. It's right here. And if I multiply it by the right-hand numbers, I'll be done. That is x, y, z. It is equal to the inverse matrix, 1/2, 1, negative 1, 1, negative 2, 2, 0, 1, 1, negative 3 times the right-hand side numbers. 3, 1, 1. Well, when you say, here's my 1/2 in front. When you dot the first row with the first column, you get 3, -2. 3 minus 2 is 1, plus another 1 is 2. And then when you dot the second equation, second row with the first column, you get -3 plus 2, which is -1, plus 1 more is 0. And then you dot the third row with the first column. You get 3 plus 0 is still 3, minus 1 is 2. And then you multiply each of these three numbers by a half. Half of 2 is 1, half for 0 is 0, and half of 2 is 1. And there is your answer. Let us try one more. This time we'll actually calculate the inverse. I did promise we'll calculate some more inverses. So basically, to use inverses, you take the coefficient matrix, you find the inverse, and then you multiply it by the right-hand side, and you have the values of each variable. Suppose you have x plus y plus z. You have x plus z. You have y plus z. And this is 3, and this is also 3, and this is 1. Now, sometimes you can look at a system of equations and see what's going on. That is, you can see the answer. Let's look at the first two equations. Here you add x and z, and you get 3. Here you add x and 3 and y, and you still get 3. This means that y must be 0. Y must be 0. The third line says that y plus z is 1, but y is 0. Oh, that means z is 1. Z is 1. And the first equation said if you add all three letters, you get 3. Well, 0 plus 1 is 1. You add 2 more, you get 3. X must be 2. Or you could have said x plus 1, because z is 1, is 3. And you all know that 2 plus 1 is 3. X is 2. So sometimes you don't have to do any of this. But I must admit, if it says on an exam, solve by using inverses, you can't use the technique that I just showed you. Sometimes if you think, you should always think about a problem before you do it. Maybe there's an obvious answer. Unless they say use inverses, and then even if there's an obvious answer, you have to use inverses. Coefficient matrix. 1, 1, 1. Sorry, 1, 1, 0. That's the coefficient of the x's over here. The y's. The first equation has plus 1y. The second equation has no y's. The third equation has 1y. Z's. The first, second, and third all have plus z. That is 1, 1, 1. Now, I need to find the inverse of this matrix. And then I'll multiply it by 3, 3, 1, and I'll know what x, y, and z are. So we augment this with the identity matrix. And then we get it into reduced row echelon form. This entry is non-zero, which is good. I want to get what's beneath it to be 0. That is, I want to get that 1 to be 0. So I'll just do row 1 minus row 2. The first row, no change. The third row, no change. The second row, subtract. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 0. 0 minus 1. And then 0 minus 0. Okay. Column 1, complete. Now we need to deal with getting zeros above and below the first non-zero entry in row 2. Well, they're all 1s. All 3 entries are 1. We'll just do row 1 minus row 2. After all, 1 minus 1 is 0. And we'll do row 3 minus row 2. After all, 1 minus 1 is 0. So the second row is not being changed. And we do row 1 minus row 2 for new row 1. 1 minus 0. 1 minus 1 is 0. 1 minus 0 is 1. 1 minus 1 is 0. 0 minus negative 1 is 1. And of course, 0 minus 0 is 0. Now row 3. New row 3 is row 3 minus row 2. 0 minus 0 is 0. 1 minus 1 is the 0 that we wanted. 1 minus 0 is 1. 0 minus 1 is negative 1. 0 minus a negative 1 is plus 1. And 1 minus 0 is 1. This here is the identity matrix, which means, so if I call this matrix here A, well then there's my A inverse. There's my A inverse. I didn't even have to scale out anything. The only thing is I don't think that's right. Shucks. Somewhere there seems to be a mistake. Everyone is laughing at my arithmetic skills. Just give me a moment. We will find it. We probably have no error. We probably have no error. This is not the identity matrix. I need to, using this row, row 3, first non-zero entry, kill off that 1. I'm just going to do row 1 minus row 3. 1 minus 0. 0 minus 0. 1 minus 1. 0 minus a negative 1. 1 minus 1. 0 minus 1. And the second and the third row, they stay the same. Now that this is the identity matrix, this here is the inverse of what I called matrix A. Okay. So now I take the inset x, y, z is equal to the inverse 1, 0, negative 1, 1, negative 1, 0, negative 1, 1, 1 times the right-hand side numbers, 3, 3, 1. We erase some of this, and we'll do the multiplication carefully. We take the first row, 1, 0, negative 1, and we dot it with the first column, the only column. We get 3 plus 0 is 3, minus 1 is 2. X is 2. We take the second row and we dot it with the only column. We get 3 minus 3, which is 0, plus 0 is still 0. We take the third row, dot it with the first and only column. We get negative 3 plus 3 is 0, plus 1 is 1. X is 2, y is 0, z is 1. That's how you solve a system of equation using inverses. It's a piece of cake. That completes this section.